So we will start basically writing the macro command. The first thing I have to do is basically redirect the my files directory, because if you remember from the syntax video, we'll know that the macro processor will by default look inside the FactSage installation folder, which is typically CFactSage or CFactSage WS. So regardless of what you did in the Equilib module, so we changed the my files directory in the Equilib module to C workshop DS, but the macro processor is not going to consider this. So we need to indicate to the macro processor that the my files directory is not the FactSage installation folder. So to do this, we use this reserved variable %dir, and then we give the path to the default FactSage directory that we want to use. Okay, this is a reserved directory which is already created for you, so you don't need to declare it. So here we're going to write %dir equal to C, so we need to give the entire path, C / workshop, and then DES, I think I put like this. I can check very quickly. Yes, workshop DES. Okay, and \. Okay, so this will tell the macro processor to look for the files, save the mixtures, and anything that we have to save or open has to be looked in there, unless I specify a different path to that file. So we need now to tell the macro processor that we want to basically connect with Excel. Okay, so we need to define OLE link. If you remember, we can look in our command sheet here. The OLE link commands are created here. So the first thing to do is to create the OLE link, and for this we use this command. So we have OLE, and then we add the number from n equal to 1 to 1. So to be logical, you can use only 1, but it's not necessary. You could use only 9 or only 7. It's up to you. It doesn't have to start with 1. And then we have to give the file name with the extension and then the sheet name. Okay, so in our folder, our Excel file is called DES example. It's the XLSX file. So DES example plus the extension XLSX. And then inside the XLS file, I changed the sheet name, so now I have to put the actual name that I changed, so it inputs. Okay, inputs. So this is basically declaring or creating the link with that Excel file in that worksheet. And this will say where to find this. After that, I need to basically use some variables to store the values here for the macro processor to access them. So I will need a couple of variables. So now I'm going to define some variables here. I'm going to use one variable for the hot metal composition. So all the user variable start with %, so I have to indicate this %. And then I have to give a name, which is kind of meaningful for me, and it was have to be non-ambiguous. So %hm, for example, comp, for composition. And then I can basically take everything at once. So I know that the composition of hot metal contains 4 elements, so I can basically store them in one array or one vector here with the size 4. Okay, and then I need the hot metal mass. So this one I will create a different variable to contain the mass, which is now a simple variable. So it's just one entry in one variable. Then we do the same with the slag composition. So I will name it slag comp. Okay, and then this has only 3 entries. So this variable will have 3 entries. And then we also have the slag amount, or slag mass, for example, to make it similar to the hot metal mass here. And then we have 4 conditions here, process conditions. Okay, I can make a second line of variables, so you can have more than one variable declared. You can have several variable lines for the declaration. It's not a problem. So we have the temperature. So we can call it temperature, for example. Only one entry. And then we have the duration. And then we have the hot metal reacting here. So we can name it hot metal reacting. And another variable for the slag reacting. Okay. Reacting. Okay. So we have created these variables for basically storing the values from Excel. So now we can basically call the OLE link to store this variable. I'm starting to write a lot of commands. So to make sure I'm not losing anything if something happens, I will save already this. So I need to save that macro file as a .mac for FactSage to know that it's the actual macro file. So I will save as, file, save as, here. I'm already in C Workshop DeS. If you're not, well, you need to navigate in your computer to find the folder to keep everything together. But it doesn't have to, but it's easier if everything is together. And then I'm going to name it DeS, for example, desulfurization of hot metal. It's up to you, okay? I have to add the .mac extension here to make sure that my text editor, instead of putting text, will make a .mac extension. And then to make sure of that, I will use all types so that it does not add on the .txt to my .mac and make something really weird. Okay, so I just set up like this. Okay, and then I will save it. So in the case of my Notepad++, I have associated .mac towards like some syntax highlighting. So some of the commands here, like OLE and variable, will be highlighted. So it's a bit easier for me to see whether I'm making a typo with the variable names, for example. Okay, so I've created this. Now I'm going to read the inputs from the Excel into these variables. So I start with the hot metal composition. So I will call the variable. We can also have a look how to read a value. So the commands here is like that. So read the value of worksheet cell B5 into the variable. So first I'm stating the variable. It has to be a user variable. Then which OLE link, and then the label read, and then the cell address. Okay. In the case of variables with several entries, I can take advantage of the fact that microprocessor will automatically copy like cells next to each other to fill up a variable which has more than one entry. Okay, so if I want to do it perfectly right, I would have to see in the first entry of hot metal composition, you have to go to OLE1, then you have to read, not write, and then I have to give him which cell. So the HM comp 1 will be iron, so I have to give him A3. Okay, and then I have to do it the same, for example, for the carbon. So I have to go to second entry and then go to B3. The thing is that I can go a little bit faster with this because automatically the microprocessor will look into the adjacent cell to fill up the values. So I can tell him to take the entire variable by removing the position here. So this will tell the microprocessor to take the entire 4 entries of the hot metal composition and then look into A3. And because it has a size 4, it will automatically take the range of 4, basically starting with A3. So automatically it will take B3, C3, and D3 to fill up the next entries in HMComp. So I don't need to basically to specify each entry one by one. Okay. Then I have to tell him where to store or where to find the hot metal mass. So again, OLE1, read, and then here it's going to be E3, so E3. Then the same for the slag composition. Again, it's a variable with many entries, and my data are arranged horizontally. So I can basically just give him the first entry, and it will automatically fill up the next entries with the next cells inside the worksheet. So only one, read, and this is starting at A7. Okay, so to get this, I should not specify any entry. Okay, for the slag composition, I should just give the full name without any entry, and it knows that it has going to take 3 entries at once. Then the slag composition, the slag mass, sorry, we already did that. Sorry, I didn't have uppercase here. And then only one, read, and then the value here is to be read into E7. Then we have the kind of like process conditions here. So we need the temperature, which is only one, and read, and then the address, just click on it, see it's H2 for the temperature. Then the duration, so only one, so it's very repetitive. If you know how to do it, then it can be really fast, or you can just copy paste if you like to. So H3, and then hot metal reacting. So I can also select it here, which is the nice thing also with Notepad++, instead of having to write everything again. Only one, and then read. It remembers what I already created before. Hot metal reacting, this is H5. And the liquid slag %, so slag reacting here, only one, read, and then H6. Yeah, so H5 and H6. Okay, so we have read all these values here. Of course, the microprocessor doesn't care about about the headings, so this is only for you to know where you store these values. The only thing it's interested in is basically the amount and composition and everything that used to be here. So obviously, if you change something in here, so for example, if you decide to move this down or to add a new column or change the rows and something like that, you need to update the addresses here. So the microprocessor or the code here does not follow what you did in the meantime inside your sheet. Okay, so you have to make sure that if you change something here, then you change it something here there. Otherwise, it's not going to read the correct value or the value that you think. Okay, so we read everything here. Now we are ready to basically open the equilibrium file that we created and basically change the values for the reactants and change the conditions and create the streams. So we start with the hot metal. So we need to find the command to open. So this is in the very first one. So this is the command to open an equilibrium file. We have open, then the file name. If it's not inside the my files directory, then we have to put the path, and then we have to specify the extension .equi. Okay, so we go here. We're going to tell him with open to open hot metal init from our folder. Sorry. You have to respect how you wrote it inside your folder. That's why I put the folder next to me, so I remember how I wrote it. Open this. So this will basically open the equilibrium file with all the conditions, so the reactants, the phase selection, the database selection, and the final conditions that are stored inside this. Okay, and now we can basically start changing the reactants amounts, for example. So we can go in our summary sheet here to find out how we change the mass of the reactants. So we have to use the set command here and use these variables, set reactant, and then we have to list the reactant number inside the reactant list, and then change the mass. We can also change temperature, pressure, but here we are interested only in the mass, and then we have to give the new value. Okay, so I'm going to make it here, set reactant. If we are not sure anymore how we define the reactantness, it would be a good idea to basically reopen the file here, and then check. So the first reactant was 1, set reactant 1 was iron, and then we want to change the mass of iron from what we obtained with from the worksheet, the Excel worksheet. So we need to basically consider the composition and the total mass. So we need to make mathematical expressions to multiply this by this and divide by 100 to get basically the mass. The microprocessor will not consider composition and the mass separately. You have to calculate by yourself what is the actual mass based on the composition and the total mass of the phase. Okay, so here we need to use a mathematical expression, and the only way to do this is to use the function $mat. Okay, so the microprocessor cannot do this kind of mathematical expression outside a function. So there's a special function to call for making even just additions or multiplications to do. Okay, so we need to call the math function. Okay, so the value can be a function, so we can directly enter it in the value. Then we open the bracket to start the mathematical expression, and we need to make the mathematical expression. So we need the hot metal composition, and we need the first position in this. So you know that this has 4 entries, each entry being basically these elements here. So for the iron, we need the entry number 1, okay, and then we need to multiply it by the total amount of iron, which is defined here, which is our hot metal mass here, because we saved that value inside this variable here, and then we divide by 100, because this is given in the weight percentage, so we need to divide by 100. And this is for the reactant 1, and we have to do it for each reactants. For the reactants number 2, we would copy that example to go a bit faster. So this is entry number 2, which is carbon, if you look at our thing here. And then change also the entry of the hot metal composition. If we don't change it, then obviously we're going to use the iron for the carbon, and it's going to make a big problem. So we need to alter this. So this is an interesting way if you don't have that many reactants. But if you have like many reactants, like 50 or so, then you will have to copy this 50 times and change every time. So we can be a bit more efficient here and use, because it's repetitive and it's incrementing every time, we can use basically a loop to do this. So we're going to look at the loop functions here, how they work inside microprocessing. So this is how the syntax of the loop starts. So we have a loop variable, and then we have to define what's the starting value and the end value. And we can also put an increment value if you want. If we don't, then it's 1. And then the variables or the commands that needs to be repeated. Okay. So here we have the same command, which is this command, to be repeated a certain amount of time. So basically here 4 times. We need to change the 4 first reactants in our equilibrium file. So I'm going to use a variable for making the loop, and I'm going to use usually this person1 to person9, which you remember in here, are pre-declared user variables. So you can access them, you can change the values anytime, and they don't need to be declared. They're already ready for you. Okay, so I don't need to declare it. Usually I like to use these kind of variables for these kind of loops because I don't need to keep up with the value later on. So once the loop is finished, I don't need to know what is person1. So it will go from 1, so the first reactant, to the 4th reactant. Okay. So every time that the loop is executed, then the person1 would change from 1, 2, 3, and 4. Okay, so now I'll change this value. This is the command I want to repeat, and I will change here. So this will be changed every time, and this will be changed every time. So this will be incremented at each loop. And then this is the only command I need to repeat. So I can basically close my loop, and this is how we close a loop. We repeat the loop variable and then the label loop in all uppercase letters. And then it will repeat this block 4 times. So basically change every time the reactant number. Okay? So we have changed basically the quantities here. The other quantities are already 0, so we don't need to touch. If you want, you could make sure by adding set reactant 4, set reactant 5, and set reactant 5 and 6 and 7 to be zeros to make sure if you want. But here it should not be changed because it's already set up as zeros inside the original equilibrium file. Then the last thing we need to do, we already made a phase selection and we don't need to change that. So the only thing we need to do is basically change the final temperature. The pressure is going to be constant. Okay, so we need to find basically the command to do that. So if we look at our table here, this is the command with the set command, how we change the final equilibrium temperature for the equilibrium calculation. So set final and then T for the temperature and then the new value. Okay, so we're going to use this set final T, and then we need to basically take the value that was written in the worksheet. So we need to use the variable that is now containing this variable, which is percent temperature here. Percent temperature. So here, with these commands, with these lines, we change the reactant mass for all of them, for each 4 reactants, and then we change the final temperature. So we change the conditions, so now we can basically do the calculation. So the calc command is basically like this, only 4 letters, and it will tell basically to calculate the equilibrium conditions with the changes that we made, or other changes will be taken as it was into equilibrium file. So once we have calculated, we need to basically save the streams because we need that solution FELQ to be used in the other equilibrium file. So we need to save that, and then we can see how to save streams is using the save command here. There's different type of species that you can save by basically changing the label, the last label. So if you want to save the gas as a stream, then you use this command. If you want to save all the solids, then you can use this. If you want to use save all the solutions, then you use this. And then if you want to save a specific solution, which is our case here, then we need to use this, basically this command, this syntax. So first save, and then the name of the stream we want, followed by the extension .mixed, and then we need to specify the database nickname, and then hyphen, and then the database, the solution nickname here attached together. So we have save, and then let's call our stream hot metal to make it understandable. Then the extension, tell it that we want to save a stream, and then we need to specify which phase. Okay, so here it's going to be F2 miscellaneous FELQ. If you're not sure about how to find the nickname, you can see that it's actually written here. So FT miss hyphen FELQ. Okay, so you can take this base and phase as your nicknames to use for saving the streams. Okay, so FT miss FELQ. Okay, so with this command, anything that is calculated here will be saved in a mixture file and can be used later on in another equilibrium file. Okay, so we are done for our hot metal initialization. So we change the reactants, change the final temperature, and save the streams. So we are done. We can go on with the slag. So we do it basically exactly the same. It's a different equilibrium file, so we need to open it. So we can check in our folder. This is slag init, so that's why that's the one we need the macroprocessor now to open. Slag underscore init, and then we don't forget we have to add the extension, so .equi in this case. Now it would be a good idea to basically reopen it to make sure of the order of the reactants, to make sure we have the same order. And then we can use something similar than the one that we did with the hot metal liquid. Here we have only 3 reactants, so it doesn't really matter. But if you had a lot of reactants, it's much more efficient for writing to use this kind of loops than having to write this command many times and copy paste and having some errors maybe coming in there. So we're going to use this kind of writing here. So I can use person1 again because I don't actually need to store it. And then this time it will go from 1, so from reactant ones, 1, 2, and 3. So 1, 2, 3. Okay. Then we have to put the commands that we need to repeat. So in this case there is only one. So we need to change the reactant amount, set reactant. And then we need to define the reactant places. So this is the thing that is going to change at every loop. So this is person1. Then we need to change what? We need to change the mass. And then we need to tell what new value should be used. So again here, it's going to be the same something similar than for the hot metal, because we have the mass composition, the slag composition, and the slag mass. So we need to make a mathematical expression to take the mass of each component based on these two variables. So we need a mathematical expression. So we need the $mat function to call, and then we need the composition of the slag comp in this case. Then we need to specify which entry, because this is a variable with 3 entries. So we need to specify which entry has to be used. You cannot use 3 entries at once. So here we need person1 because it will change at every loop iteration. And then we need the slag mass. Oops. Slag mass here. Okay. And then because the slag composition is given in weight %, we need to divide by 100. Okay. So this is and then we need to close the parentheses for the $mat function, otherwise it will complain. So our loop is finished. This is the only command that needs to be repeated. Then we basically close the loop with this person1 and then loop. So we finished with the reactants. It has to be uppercase letters, so I need to put back to uppercase letters. And then we need to change the final temperature. It's going to be exactly the same temperature, so it's isothermal and all the phases are the same temperature. So I can just use exactly the same command as for the hot metal init.equi. Then when I change the reactants amount, I change the final temperature. I can do the calculation. Okay, so this will perform the calculation with the given conditions. And then once I'm done, I can save the streams. So here, if you remember, we have we basically create 2 streams at once. So we create a stream for the solids, and then we create a stream for the liquid slag. Okay. So we're going to first create the stream for example, for the liquid slag. So here you see how it should look like. So it's similar to there, so we can save, and then we give a mixture name, different from the other one, obviously. And then we specify the database nickname, and then the solution nickname. And then in a case like our case where we have the I option, we have to add at the end pound, and then which number of the solution to take, because here there will be, because it's a I option, there will be 2 slag A, and then we need to specify which one. Okay, we're not interested in the slag A number 2. It should not form in the present condition for the hot metal desulfurization. So we're going to save our slag. So I'm going to call it slag, not to make it too complicated. And then I have to specify the extension. next to tell the microprocessor that it has to save a mixture file, not a text file or anything else. And then I have to specify what phase I want to put in. So here again, I can just look at the name here to see how to use it. ft exit hyphen, and then you can put all if you want like this. And then it's an I option, so I have to put the pound and the 1 to say that I want the first one of the two that are created from this. So this is one, the liquid slag. Now I have to save the solids. So for the solids, there is only one way, is to use this. So you cannot save one solid in one stream. You have only the option to save all the solids in the streams. And the syntax is here. So it's very similar, except that instead of using database and phase or solution nicknames, you just write solids. Okay, so here, and then I can just call it solids. Doesn't have to be very complicated. And dot mixed. Okay, for the extension, very important. And then I have to tell it what I want to save in that mixture file, which are the solids. So I put solids here, and it will save all the solids. So the 48 solids that I've selected here into that stream, okay, with their mass and anything that is relevant for the equilibrium calculation. Okay, so this is basically the first part. We have created the link, so we have told the microprocessor where to look for the files. We have created the OLE link, and then we have declared a certain number of variables that we're going to use later on. And then I have basically read all the important values from the Excel file and store them in different user variables. And then I've opened the initialization equilibrium files one by one, change the reactants, change the final temperature, make the calculation, and save the stream for the hot metal, the slag, the liquid slag, and the solids. So now I've done this, we can test it. Okay, so if you remember from the video, there is only one place inside Equilib where you can start the macro, so the macroprocessor. This is from the reactants window. Okay, so inside the file menu, we have a macroprocessing submenu where you can run the macro. We have two run commands, if you remember. The first one is basically a kind of like shortcut to the last macro that you run. And here, because I deleted it, it's not available anymore. So we have to go to the second run macro, which is where I defined what new macro to use. So I'll click on the second one. So we have a new window here. And then I can browse to find my macro file, which I just made, which is DeS hotmetal.mec. I see here it's red. I forgot to save it. I should save it first. Otherwise, anything I've written will not be actually included in the commands that will be sent to the macroprocessor. So here, just browse it again to make sure it actually took the right position. Browse, and then use the DeS hot metal here and click open. Okay, and then once I click OK, the microprocessor will start. Okay. So you see that it took control of Equilib, start opening and going through the pages, and start changing everything. And then all the commands that it actually did are written in the macroprocessing status window here, with all the basically each commands that I stored here, and read all the things here. So the important thing that you should look at is basically figuring if it read the values from the worksheet correctly by just looking quickly. Here, slag mass is 5, duration is 10, slag rating is 30, which is what we wrote in there. Another interesting thing that we can look at is the pause command, which is like shown here. Very interesting. It's going to pause the execution of the macro. And the interesting thing here is that you can actually check what the microprocessor has done to the equilibrium file before it moves to the other one. Okay, so we're going to add this pause after, oops, not pause, after each calculation. Okay, so I can see at that point how it changed the values and what are the results to see whether they make change. So I will save that and then go back to my reactance window to start again, to run it again. So run. Now my previous macro file is selected here, so I don't have to, I just click on this and it will start automatically. So you see here, it has gone into pause. I'll just make it lower, smaller here. It went into pause, so it's actually asking me whether I want to continue or to terminate. And it has shown me basically the calculation that it just did with the calc here. And then I can navigate here to see whether basically the temperature has been changed and also the quantity has been changed as I want it, okay? To make sure that maybe I forgot something here, that everything is the same value, or it hasn't read correctly the value. Maybe I put the wrong address, so it didn't take the right value. But here everything is fine, so I can just go to see the next one. And here is the slag. So I have 3 CaO, 1.25, 0.75, no iron, no sulfur. So I have 5 tons in total, which seems to be okay. I can go also check if the temperature is fine, the phase selection is still good, and then the amount that I choose is basically according to what I entered in here. So everything is okay. Okay, so this is the good thing about pause. The next thing you should look at is whether the streams have been saved correctly. Okay, so if you go back to your the workshop DeS folder, and you should see that some mixture file, so if I look at the types here, mixture file have been created inside inside the folder. Okay, so we have the hot metal, the slag, and the solids. So here the mixture file has been created correctly. I can show you, for example, the danger here about save is that it usually does not complain if you make a mistake. So for example, I will make a typo and forget to put correctly the right name, for example, for the solution, and save it, and you will see that the microprocessor will not complain, which is a very dangerous case. Of course, I forgot to remove the pause, so we have to just tell him to go. So you see that it does not, stop anything, because for him it's not a mistake per se. It just didn't know what to do. So here we told him to save FT oxide slag A, but in reality there's pound 1 and pound 2 because there are 2 slag because of the I option. But here we forgot about it, and then we forgot to put the pound 1. But instead of stopping and telling the user that there is a problem with this command, couldn't find slag A, it does not do that. It just basically go to the next command without saying anything. And then you can see, if you don't look at it carefully, that these streams actually have not been created. So only solids has been created because there is no typo. And I made a typo also in the FT miscellaneous FLQ database. Also, it does not give me any warning that something wrong went with this command. But instead of saying something, it just does not create anything. So here I'm missing the hot metal and the slag solution. So you have to be really careful here to not making any typos, and then systematically checking inside the folder if the streams have been created. If they haven't been created, it means that you probably made a typo and you have to look again if everything is okay. So here I correct sorry, I have to run it again. So I corrected the typos. So now the solid, slag, and hot metal streams have been created correctly. I'm going to remove the pause here because now I know that these two equilibriers are being done correctly. So there will be no problem with this. So we are basically finished with the this step. So we can move to the next step. If we go back to here. So we have prepared the equilib files for the initialization and save the streams, and we wrote the command for that, and we made sure that they work correctly. So the next part is basically prepare the equilib files and write the macro code for the process reactions itself. So this is where the flow sheet becomes very useful because it literally already lists all the reactants and products that need to be specified in the equilib files. Okay, so we'll do these ones. We'll go back to equilib. We'll start with reaction 1. So I will have my flow sheet here. Try to make it a bit bigger. Again. Okay, so our first reaction, we have basically two reactants. One of them is the hot metal, and the other one is the slag. So we're going to make a new reaction, clear the current system to get no reactants, and then we're going to add the hot metal and the slag. So these are actually in our system, these are streams that we just created with the macro processing. So we have to import the streams as our reactants. So for that, we go to the menu Edit, and then there is a menu Mixture and Streams. And then we have a submenu for importing a stream. And then you see here that the streams that are already created inside that folder are listed here. So we just need to select which one we want. So we're going to select the hot metal first. So we click on it. And then the hot metal stream that we just created has been imported. Then we do the same for the slag, mixture and stream, import a stream, and slag. Okay, so we know that from our assumptions in the reaction 1, the solids are not taking part. So these are the only two streams that we need here. Okay. So as you can see, when a stream is imported in the reactants, so equilib put the default value for the quantity as 100%. So that means that the total mass which is stored in the stream file will be used. So you see when you hover over it, at the bottom there is hot metal and then 100 gram, so which is the amount that we defined when we created that stream. Okay, so if you put another value, like 80%, for example, and then you hover back in it, you will see that 100 gram was already defined in the stream, but then I take only 80% of it. So in the end, there will be only 80 gram taken as quantity for this value. You can also not use percent and put 1000, for example. It's not a problem. It can be higher than the amount stored in the stream. In that case, then it will not look at the actual amount that you stored inside the stream. It will just look at the composition and use the quantity, the absolute value quantity that you use. So basically the quantity value here stored at a percentage is very useful because it does not require us to keep up with the actual amount of material in the code. I can just put 100% as being quantity, and I will be sure that whatever amount was saved in the stream file is going to be used. Okay, so for here example, for the slag, we have 1.57298 being stored inside the liquid slag, okay, which is very useful because I don't have to manage that value. I can just manage the percentage to get a certain fraction of it. So in this case, I will leave the quantities unchanged because the macroprocessor will modify both entries during the simulation. So I don't need to take care of that at this point. I will check the units again And we are in Celsius, ATM, and grams, so everything is fine. We go to the data search for changing the database. We're going to clear everything. And then in this case, we have both the hot metal and the slag. And then we know that we're going to have hot metal and slag as being products. So I need to select the FT oxide for the slag and the oxide, the solid oxides. And then I need the FT miscellaneous as well for the FeLQ. So both of them together. Okay. Once I'm done with this, I can click next to go to the phase selection. And in the compound species, I will select all the pure solids, but I will see here that actually I'm not at 48 anymore because I have basically 2 databases selected. I could have some solids actually coming from both databases, but I want only the solids from FT oxide. I'm not interested in the solids from FT miscellaneous. So I will select, I will right click on the plus option, basically to open the list of species that have been selected. And I see that indeed it selected everything, and it took some FT miscellaneous solids here, which I'm not interested in. It's sulfide and pure and sulfides, sulfur and sulfides, which I'm not interested in here. So I will clear by using the option on the bottom, using select and clear. So I will select this, and then I'm going to remove all the species from the database FT miscellaneous. Okay, so I will keep only the FT oxide compounds. Okay, so this is automatically removing FT miscellaneous solids here, and then I can just click OK, and my solids are back at 48. Okay, then I select the FeLQ, so that will create our reacted hot metal solution. This pure solids will create our reacted solids, and then I need the slag. So for this one I have to go down to see the FT oxide solution, and then my slag A is here. And I will keep the I option here, and then I can click on the selected here to see only the phase that I selected. Okay. The final conditions are the same as before. So we need a fixed temperature. We don't worry about the value right now. It's going to be changed by the microprocessor, and then the pressure should be ATM, and the last field must be empty. Okay. Then I can save this Equinix file as being R1. Okay, so I will save as and write it at R1. Okay. Okay, so this is going to be reaction between hot metal and liquid slag. Oops, slag. Okay, it's a comment just for remembering what was the reaction about, but it doesn't have to. Okay, so I've created R1. Theoretically, I would be ready for R2. The only thing is that you see in the flow sheet that I would need the reacted hot metal stream to be created here. But in this case, I don't have it here. It's not there yet. I just have the bulk hot metal, the slag, and the solid. I don't have any of these 3 streams, which must be theirs because they are different from the hot metal, the bulk hot metal, and the bulk slag, and the bulk solids. So they have to be 3 additional streams to basically keep up with this composition and these amounts that are different from their respective bulk phases. So there are 2 ways to do it. Either I can go with this, basically make a kind of like random calculation, and then I can basically save these stream files manually by using the output. So you have an output stream file, and then you can save the stream files one by one. I would create these stream files for the solids and the solutions. I would go for one for FeLQ and another one for slag A, number 1. Okay, so I would have to do it 3 times to get the 3 streams. Or we can write the code for that reaction and execute the code so that the streams of R1 are created by the microprocessor. So they are both correct and would eventually lead to the same thing, but I have a preference for the second way because it will allow me to write the code already and make sure that the piece of code that I'm writing for R1 is already tested and executed correctly. So I will go to the macro file and continue writing the code for R1 only. Okay, so we keep on our same code. So we are now in the core of the process where these three reactions are repeated. So if you look at our flow sheet here, so these three reactions will be repeated a certain amount of time, which is the duration of the process. So in programming, the repetition of a block of code is done with a loop. Okay, you could also just write the block like 10 times, but if you want to make it 15 times, then you would have to change the code every time. So here I'm going to use a loop and repeat it a certain amount of time, which is going to be the process duration. So we go back to here to see how our loop is created. So we already made a one. You know already more or less how it works. So this is the syntax. I need a variable basically to keep up with the loop, how it changes. So I will use this time a user variable because I want to keep it up. And then I can use whatever name I want. So here I will use it as count, okay, which will go from 1, okay, the first time step, and then to the end of my process, which is basically given by the duration. So the final value will be percent duration. And in this case, I'm kind of assuming the time step is 1, so I don't have to specify the step here. It's going to be default 1. Okay. So if duration is 10 minutes, then it will make the loop 10 times. 1 minute being the time step. Okay. I'm using a user variable which is not pre-declared, so I have to declare it before using it. Otherwise, the macro processor will complain and stop there saying, I don't know what it is. Okay, so I have to declare it here, person count. Okay, to make sure I'm not making a mistake, because now I have a lot of code to put into this loop, so I will already close it. Okay, and I will add on the code in between so that I make sure that I don't forget to actually close the loop. Okay, so I close the loop with this syntax. So repeating the loop variable and then the label LOOP, loop, in uppercase letters. Okay, and then basically I will add on the code that needs to be executed like a certain amount of time. So in the first one, we'll have to open and execute or kind of calculate the equilibrium for R1. So again, I have to specify to the microprocessor which equilibrium file to open. So I will give him, this is open r1.equi. Never forget the extension, otherwise it will not find the file. Then I have, like the other cases, I have to change the reactant values. Okay. So I will use the syntax for that. It's the same as here. Set. I have only 2 reactants and they are not really matching each other. So I will have to just write the reactant change command for each of them. So set reactant 1. If I open, or if I go back to my reactants, the first one is the hot metal. And this one, because I'm here in my flow sheet, there's my flow sheet here, you see that it should be the Y amount here, or the percentage that I used, which is in my worksheet, this value. Yeah, this is 20%. I want 20% to be reacting in R1, and I want 30% of slag reacting in R1. Okay, so I have to put this value 20% in the reactant 1. So set reactant 1. I will change the mass, and then I have to put this value. And this value is stored in the macro code in this variable, which is the hot metal reacting. So I will use this and put it there. Okay, so this will take the value. But here you see that the only thing which is written here is 20. So we have to tell him on top of that that this is a percentage. Okay, so I will just add the string %. So when the macroprocessor will read this, it will replace this with the value that it has read from the worksheet, and then it will attach the character % at the end. So when it actually fills it here, it will put 20 and then % to use the % kind of like way of writing. So it will take 20% of the amount that is saved inside a string. In this case, it's 100, but if you do the calculation maybe 5-6 times, it's not going to be 100 anymore. It could be less or it could be more. Okay, so it will keep up with the amount stored inside the stream hot metal. Then we have to do the same with the slag. Set reactant 2, and then we change the mass. And then we do the same, except that, of course, we are looking at the slag reacting, not the hot metal reacting. So we enter this variable, slag, and then reacting. Okay, and then again, because slag reacting is actually contain only the value 30, and we want 30%, we attach the string, the character % to, so there's no space, you have to attach it directly to the stream name, and it will append % to the value inside slag reacting. Okay, so there's only 2 reactants, so we are done with changing the reactants. Then we have to again change the final temperature. Here we don't have anything else to change. All the phase selection is already saved inside the file. And then we need to change the final temperature. So using the same, basically same command as before. So I can just take it and paste it here because it's always the same value. It's isothermal and all the phases are the same temperature. Okay, then when I've changed the reactants value and the final temperature value, then I can basically calculate. Okay. Once I've calculated, I have to save the streams. So I have to save, if you look at I have to save these 3 phases in different streams because they are going in different directions. So I have to have a stream for the hot metal, a stream for the liquid slag, and a stream for all the solids created here. Okay, so I have to make a streams different from the bulk. So I should not use the same metal as hot metal.mixed, otherwise it's going to overwrite the hot metal, and then I will not be able to find what is the bulk hot metal anymore. So I have to make something different. So hot metal reacted, for example, to keep it, to know that this is the hot metal, and this is after reaction, and then don't forget the extension, and then I have to specify what phases to put in. So here, this is the FT miscellaneous FELQ solution to put there. FT miscellaneous. Don't make a typo, otherwise it will not create it. Okay, so this is my FELQ for my hot metal reacted. I have to do the same for the slag. So I will name it slag reacted, and then add the extension .mixed, and then I have to put the name as it appears here. Oxide hyphen slag A. Once again, you have to be careful here because there's an I option, means that there will be 2 slag A generated after the equilibrium reaction. There will be a number 1 and number 2. So here I'm interested only in the number 1. So I have to put pound and 1 to save only the first slag A. And then I have to save the solids. Again, save. I can make solids reacted to kind of keep with the same structure of name as before. And then I'm saving all the solids. So for that, I'll just need to write solids. It will basically store the 48 solids inside that mixture file. Okay? So once I'm done here, I can run it. I will again put a pause command after calc to make sure that basically the things that I wanted to change inside the equalib file are changed correctly. So this will allow me to see what the equalib file is after the calculation. Okay, and then I will also put the end here to basically not having this repeated like 10 times, because I'm not interested to run it 10 times. When the microprocessor will hit the end here, it will stop, even though there are still some commands and even though the loop is not finished correctly, because I'm not interested in like doing it as many times. Okay, so once we're ready, we have to save, of course, and then we can run it. Here I was going to make a mistake. You see that I'm not in the reactants, so the macro processing menu is not here. I have to go back to the reactants window. Okay, and then I can just run it with the shortcut here, and it will start the macro processor right away. Okay, so now it's at reaction 1, and you can see, so I've started a loop with count, which is now 1, and then it has read correctly the values that I wanted. So it took the 20 and then added the percent before. Okay, so if you look at, and then did the same with the slag, and then if you look at actually the values here, you see that it took 20%, and then it will change. So the actual amount based on the total amount of hot metal which is stored in the stream, and the same for the slag. So there was 1.57298 grams or tons in this case of liquid slag, and it took only 30% of it, which is now 0.471893. And nowhere in the code I actually had to keep up with how much liquid slag was produced and how much liquid slag you have to put there, how much fraction of this liquid slag amount is there. So this is the advantage of using this percent compared to absolute value. If I was about to use absolute value, I would have to keep up with how much liquid slag is produced everywhere to be able to use this percentage correctly. Okay, so I will continue this because there are still 3 commands, which are actually the commands I'm interested in, is to produce the mixture file. Okay, so here it has normally created these 3 streams inside a folder, so I will check in the folder to see whether they are created correctly. If I, for example, didn't make any typo in the solution or database names or so. So you can see that the solids reacted is here, the slag reacted is here, and the hot metal reacted is here. So everything is fine with this part of the code. I will just remove this now because I already checked it, so I don't need to pause it anymore. So once everything is fine with R1, so then we can go to create R2. Okay, so I will go back to equalib, then also have my flow sheet here to see what I have to do. So reaction 2 is the homogenization of the hot metal. So I will start with creating an empty page, and then I'm just following the flow sheet. So the first reactant is going to be the hot metal, the bulk hot metal. So I go to init and then mixture in streams, import a stream, and I'm going to look at my hot metal. Okay, so that's why it's important to give like meaningful names to your streams, because once you have a lot of them and then you give them like difficult names, it's going to be really hard to find which streams you have to use. So here I put a reacted, and then this one is the bulk. Okay, so I know that this one is my bulk. And then the second stream for the reactant, second reactant, is the reacted hot metal. So again, I have to import it, edit, make sure it's in stream, import a stream, and then my hot metal reacted, which is the first one here. Okay, and I had it. So I don't need to change the quantities here. I'm actually very interested to keep this again, because here, whatever was produced in the first reaction, the amount is actually stored inside the stream. So here you see that I actually put 20, but only 19.9923 tons came out of the first reaction. And I don't need to keep it up. I just put 100% here, and anything that was created in reaction 1 will be automatically moved to the reaction 2 using the 100%. And this value will have to be changed, okay, because it's not 100% anymore. It's going to be 100 minus y%. But this part will do in the macro code, so we don't need to touch it anymore. We go again checking that the units are okay. Temperature is Celsius, atmosphere, and then the mass is gram. And then we go to data search to check our database. Here we have both, because it's the selection from the previous, so we had both FT oxide and FT miscellaneous selected. We are not interested in FT oxide, so we can unselect it. Okay, and then when we go to the next, I have to show all here. I can select only, because the product is basically the hot metal. I will basically select only the FT miscellaneous FeLQ. Okay, and then again, I will make sure that the final conditions selection is okay. So we have a fixed temperature. The value will be changed by the microprocessor. The pressure is in 1 atm, and the last field here must be empty. Okay, so this is fine for us. We can save this as being R2. So this is R2. Okay, save, and then we can give it a comment. So this is the homogenization of the hot metal. Okay, you don't have to, just to remember what that reaction was about. Okay, so we are done with R2, so we can create R3 as we are with Equilib right now. So again, we'll make empty reactants, an empty system. And according to the flow sheet here, we can find which reactants are what. So we need the bulk slag, the bulk solids, and then the reacted slag from R1 and the reacted solids from R2. So we have in total 4 reactants, which are all streams, and we need to import them. So the first one is going to be the slag, liquid slag. So edit, mixture in stream, import a stream, and then we look at our bulk slag, which is just slag here. Then we need the second reactants, which is the solid stream, the bulk solid stream, not the reacted one. So we're going to have an import stream again, and then we look for our solids. Okay, solids.mixed. Okay. And then the third reactant is the reacted slag. So mixture stream, import a stream, and then we have our slag reacted here. So we are going to import it. And then the last reactant is the reactive solid. So mixture in stream, import a stream, and the solids reacted here. Okay, so we have our 4 streams here. All the quantities are given in percentage, and then actually I will like them to stay like this. So don't change the value there, so that I don't have to keep up with the actual values. 100% we make sure that whatever was produced in the reaction is going to be moved to that reaction. So we want that like that. And then in the macroprocessing code, we will basically modify this value to be 100 minus x for the liquid slag. But we don't have to do it as here. And then we go back, check the units. So temperature degrees C, pressure in atm, quantity in grams, so are still okay. Data search. Here we have the FT miscellaneous, we can clear it. And then because we are basically homogenizing the slag, we need FT oxide. Okay. And we are good to go. So our reactants window is done. We can go to next. And then again, we have the same selection, only one database. So then I'm going to select all the pure solids, so I don't have to worry about it. It's 48, it's good. And then we select my FTOC slag A with the same I option as before. It's exactly the same as the other phase. And then the temperature field should be entered pressure should be 1 atm, and then the last field should be empty, which is all good. So we can also save this as being reaction 3. Reaction 3. Okay, and we can save it, and then we can give it a comment. This is going to be the homogenization of the slag and solids. Okay, just to remember what this reaction is about. Then we can write the code for R2 and R3 in our macro file. Okay, so I go back to my macro file. I can remove the end there because now I want it to continue. And then I can tell it to go to basically reaction 2 and reaction 3. So we're going to start with the reaction 2. So we have to open the file first, tell it which file to open, reaction 2, .equi, don't forget the extension. And then we can basically reopen it to make sure we're not like mixing up the reactant numbers. And then if you remember this one here from our flow sheet, we know that the hot metal mass in the reactant should be changed. It cannot be 100% anymore because some of it has already gone to the first reaction. So here we need to define what is 100 minus Y minus the hot metal reacting. Okay, and then the second reactant, which is the hot metal reacted, has to be 100%. So we don't need to change the value here. We just need to change the value of the reactant number 1. Okay, so we're going to change the reactant number 1 using the set reactant command, set reactant, and then this is only 1. And then we want to change the mass. Okay, and now we have to make mathematical expression using the $mat function because we need to basically find 100 minus this, the hot metal reacting. Okay, so we need to call the mat function to do that, $mat, then open the parentheses, and then this is going to be 100 minus the hot metal reacting. So it's going to be exactly the difference of the value we use in reaction 1. Okay, and then we have to close the parentheses. So this will basically calculate the value. And then we have to do the same trick as before. We have to attach the character percent to tell the microprocessor that we don't want an absolute value. We want the percentage for the stream. Okay, so we don't have to keep up with the actual value. We just give a percentage. There's no space, so you have to attach it directly to at the end of the $mat function after the parentheses. So we don't need to touch reactant 2. If you want to make sure, you could write set reactant 2 mass 100%, but it's not necessary here because it's already stored as 100% in the equilibrium file and nothing will make a change. Then, like all the other reaction, we have to change the final temperature with whatever was stored inside the Excel file. And then we have to use the temperature. Okay, so that's about it for reaction 2. Now we can ask him to calculate the equilibrium value, the equilibrium for these conditions. And then we have to save the file. So if you look at the flow sheet, the products of this is the hot metal. And this one is going to replace the bulk hot metal. So to do that, we basically use the same name. So it will overwrite the existing bulk hot metal stream with this. Okay, so I'm going to use exactly the same name as here. So I can copy that and paste it here. So it will overwrite the hot metal mixture stream here with basically what came out of there. Okay. Then we do the same for the reaction 3. So we have to tell him to open reaction 3. Reaction 3 with the extension. And then we can open it also to make sure of the reactants order. Okay, so we don't make a mistake there. And then we see that from our flow sheet, only the first stream, which is the liquid slag, because some of it goes there and the rest will go there, has to be changed because all the others are basically 1.5%. So we don't need to change them, they're already here. We need only to update the first reactant amount. So again, we'll do that with the set reactant command, and then this is the only for the first one. And then, like for the hot metal homogenization, we need to make a calculation to tell it it's actually the remaining of the slag reacting, so because it's a percentage. So we have to use the $mat function to make the subtraction. So 100 minus percent slag reacting. Okay. So this will call basically the rest of this. And then again, to tell that I want a percentage, not an absolute value, I attach directly the character percent to the $mat function after the parentheses. Okay. And then the other reactance amounts don't need to be touched, so I don't write anything. And then, like the other reactions, I have to change the temperature. And then, once I change the reactants and the final temperature, I can do the calculation. Okay? Calc. And then it's the same thing as for the previous homogenization. You see that only 2 streams are coming out, so basically a new liquid slag and new solid streams. Okay, and this one will basically replace the liquid slag, the bulk liquid slag, and the bulk solids. So I can use the same names to basically override the bulk so that it's already ready for the next time step. So I can go basically, to make sure I don't make any typos, to take the names that I created for the stackinization and then copy these commands and put it there. You can also like tab this one to make it nice aligned here. So we have the slag mixed. It's gonna be overwritten with the new liquid slag produced from reaction 3 and the solids from reaction 3. Okay. Again, to make sure that this part of the macro code works well, we can put pause after the calc to make sure that what we want it to be changed are changed correctly. Okay, so that it took our calculation and our percentage character correctly to make sure we don't have a mass balance problem in here. Okay, so we can save. It's red, so we make sure it's saved, and then we can run it again. So again, reactance menu, file, microprocessing, and then we have our shortcut to this macro. Okay, so it's running. You can see it's taking care of equilib, opening, calculating, moving to the next one, and then here it's going to be stopped. So we are already at reaction 2, and then we can see what it's doing here. It's like show that command here, and then it's going to start with calculating the $mat function, which is 100 minus 20, so it's 80, and then it attached the percent character at the end. Okay, and then it puts 80% inside the reactants number 1. So you can see here it actually took 80%. Okay, so it's going to take 80 ton correctly. And then also the final temperature is 1400, so it's perfect. We can continue. I also take the advantage here to see whether the save hot metal.mix is going to work well, because I'm taking some time here. I can see that the hot metal timestamp is at 8:30. So if I click go now, it should override it. And if I didn't make any typos, the timestamp for this is now 8:32. So I know that this stream has been updated correctly with this value, with this command. And then we can look at reaction 3. So here again, I gave him this command, and then it starts with calculating the value inside the $mat function, which is 70 in this case, and then it should attach the percent to the 70 to make 70%. And then we can see with the reactants window if the 70% is being actually taken, which is the case here. So we have 1.1018 being considered as being the quantity in this case. Okay, and then I'm just checking the stamp again. So we are supposed to save slag mixed and solid mixed files from here. And then if I look at this timestamp here, it should be 8:30 again and 8:30. So when I click go, timestamp should change to 8:33 about. Okay, so you see that it has actually been considered. And then we can stop it here. I will remove the pause so that it does not stop every time. And we can try to run it to see how it looks like. Of course, at this moment, I'm not printing out anything yet, so I cannot really check whether it actually gives anything meaningful. The printing of the part is the next step, but at least at this time, I can see whether there's no syntax problem. So meaning that the microprocessor is going to be stopped because some commands are not understood. You can see also because of the command here, I'm not able to. I'm kind of distracted by this equidip file, this equidip being on and off over. So you can actually click the hide button here, and then the equidip menu will basically disappear. Okay, you can already have this activated in the macro code by having the hide option, hide command, written directly inside the macro code. So that will mean that it will hide the equidip window from the beginning. You will not have to push hide. And of course, anytime you can push back the show and it will go back up, even if the hide function, the hide command has been written in the code. And then you can click it back if you're not interested to see it. This one, it didn't take it. Yeah. And that's it. So we are finished. Once it is done, you will see that the equidip window will reappear. Then you can have back control of equidip. So everything looks fine. So we don't have any major problem. All the things are saved. You can see 8:34. All the streams are saved at with the same time step, which is just the one that we just created here. So if you have one which is still at 8:30, it means that probably there is a typo somewhere in one of the save, which does not allow that stream to be, updated at the end of the loop. Okay, so once the main commands are working correctly, so we may check here, we can move to the last step of the procedure to have the results of the calculation written to Excel. So first we have to think about what results need to be printed to Excel and how to organize them efficiently. So we want to have a separate worksheet to print out the results of each phase. So we want the hot metal, the liquid slag, and the solid phases after the homogenization reaction, which is reaction 2 and reaction 3. So we are not interested in actually the reaction 1, which is like intermediate. One row will correspond to the results at one time step, and the first row in the worksheet should contain the column headers. At each time step, we want to have the current time step and the process temperature, which is here isothermal, so it should be the same value all the time. And then the mass and the elemental composition in weight percent of the hot metal after homogenization, so R2. And then we want the mass composition as species in weight percent, and also the elemental sulfur content of the liquid slag, and then as well the mass of each solid phases species after homogenization from R3. Okay, so these are what we would like to have printed in Excel to be able to follow each phases and the composition of each phases with time. So the first thing we need to do is to create a second worksheet. So we're not going to create here, we're going to organize it into a different worksheet. So here I'm going to make it a different one, and then I'm going to create and name it outputs. It could be results or anything you like. Doesn't really matter. Okay. Now I've created a different worksheet, and I want the microprocessor to communicate it with. So I need to basically make a new OLE link because it's not the same sheet. You can make the OLE link anywhere you want, as long as you basically declare it before you use it. I usually tend to actually put them together, OLE2, so I remember which OLE I have used already, to make sure I'm not using twice OLE2 for different worksheets. So this is the same file. So I basically use the same name, dsexample.xlsx, and then the sheet name is outputs. You have to be careful here because the microprocessor will not check whether the file exists. So if it cannot find the file or it cannot find the sheet with these names, it will create it for you, empty. So you think you're looking at the inputs, but actually it created an empty sheet with empty within a new file, and then everything is going to be 0. So we'll have a problem there. Okay, so this is my second link to my outputs worksheet. And now I would be interested to actually clear everything, because every time I run it, I will have results, and I want to make sure I don't mix up the new results with the results of the previous simulation. So I want to find a way to clear it. And for this one, I can go to the OLE links, and I see that the second command here is to clear all the cells in the worksheet. So just basically using the OLE link number and then the label styles, all, and clear. So I will write that in the macro command. So OLE2 cells, all, and clear. So that will clear the cells, the content of all the cells. If you have graphs, that will not delete the graphs. Okay, just the values inside the cells. Obviously, don't do that with OLE1, because otherwise everything that you wrote here is going to be deleted. Okay, so OLE1 should not be clear. Only OLE2 with the outputs should be cleared to make sure we don't have confusion between the results calculated at different time. Okay. Next, I will need a few user variables to store the results and pass them to the Excel worksheet. So if you look at how we write, the syntax is almost the same as to read. So we need a user variable to do this. And to be efficient, I'm going to use actually arrays. Instead of like having one value pass every time, I'm going to pass one variable with many entries at once to be more efficient. Okay? So I'm going to go back there. And then I will create some variables. I can probably make them at the beginning. For example, I can put them here or somewhere below. I'm going to need person, for example, person results for the hot metal. So that's for the results for the hot metal. Person results for the slag. And then person results for the solids. So I want to use actually arrays, but so far I don't know what size they're going to be. So right now I don't specify the size, and then when I'm going to write a command and know eventually what size they are, I will update the size at the declaration later on. So I will then move to the hot metal init. So I'm inside the initialization because I would be interested to know what is the composition of the phases at time 0. So before any reaction started, what is the composition? For the hot metal, it's going to be like straightforward. But for example, for the slag, it will tell what is the amount of solids, what solids are there, and what is the liquid composition at the time 0. Okay, so we're going to start with the hot metal init. So after the cal command, so I can create some headers or the column titles for my worksheet and extract the equilibrium values for this time 0. So we will start with the headers. So for example, I will just write headers here to make sure I don't confuse them. So the first header will be basically for the time. So the header will be just basically the title of each column. So I'm going to use my results HM, and in the first entry, so I specify 1, I'm going to enter the text time. Okay, so that will just basically print out the text time into the worksheet. In the second entry, I will put HM2, second entry, I will put the text temperature. Okay, and in the third entry, so I have to specify the entry every time, so this is going to be really confused. I'm going to put the mass of the solution FELQ. So I'm going to put total mass. I have to put underscore because otherwise it will not keep it together. Total mass of, and then I want to find out the name of the solution FELQ. Okay, because I'm interested now in getting the names to make sure that I'm not messing up with the numbers. So for this, we need to use the thermochemical variables. So I check in the command summary here, but they are the main macrothermical variables are all listed here, and I'm looking for the name of a solution. So here, solution K name. So this is the macro variable that I have to use for that. And then there is something, if you remember, which is a little confusing with microprocessing, is the value of K, which is the code number for the mixture. And then we'll need to find that, and it will be different for each macro file, for each equilibrium, sorry. So if you remember in the syntax video, I showed you that you can get these code numbers from the species table when you make a plot with at least 2 calculation results for an equilibrium. So I will show you now a little macro tool that will list all the code numbers for a given equilibrium. So I call it equilibcodes.mace, and it should be in the macro processing package. It's a macro file .mac, except that it has the extension mace because it's actually encrypted, meaning that you won't be able to see the commands in the macro file, but you can still, run it. So I will copy this inside our workshop DeS. It's going to be easier to find, and then show you how it works. So I execute it the same way all the macro files are executed. So I need to go to the reactants window, go to macro processing, and of course now I'm not running my macro, I need to run a different macro. So I go to run macro, I go to browse, and then inside my workshop DeS I have this getcodes.mace. So if you saved it somewhere else, then you need to basically move around to get this macro file to happen there. Then I say open and say OK. Okay, so this will basically ask me which equilibrium file I want to have the list of codes. So I have to navigate because by default it looks into the FactSage installation folder, which is FactSage 8.0 in my case. In your case, might be FactSage or FactSage WS if you're using the workshop version. Here, I will move back to my workshop DeS, so I have this shortcut already there, and then I select hot metal init. Okay, so this is the equilibrium file that I want to have the codes from. And then I click open, and then wait a bit, because it's generating the list of code numbers for all elements and solutions and species in the text file. Okay, so the text file is open here, it's already finished. And then you get this text file, which is actually saved also inside the same folder, if you need to look at them again. And then you have the list of elements with their code numbers, the list of selected solution with their code numbers. So the gas is always 1. We didn't select it, but gas is always 1, okay, even though we don't have any gas species there. And then we have the list of selected solution and their code numbers. And here, because we have only FELQ, we have only these solution. So there is 11 species in the solution FELQ. And then we don't have any compounds selected, so here we have no code numbers available. Okay. So for our case, we want the solution, the name of the solution FELQ. So we have found the thermochemical variable for that. And then we need to find K, so the code number for FELQ. And then we just need to look at our file here and see that FELQ is 2. Okay, so the basically the thermochemical variable I have to put here is $E underscore lowercase m, uppercase N for name, and then 2, because our code number FELQ is 2, and then $sign. Okay, so this is going to be the name of the solution number 2. Okay. The third, so now I can print out the name of the elements. So the third thing is like time, temperature, mass of the FELQ solution. Now I want to have basically the elemental composition of the FELQ solution, and here I want to have basically the name of each element that is present inside the FELQ solution. So to print out the names, I have to find basically the thermochemical variable for that. So in the summary table, we can look at element name. So this is here. So this is the thermochemical variable to find the name of an element I. So I, again, is the code number for the element. But inside this text file, I already know the codes and the element name for each of them. Okay, so the only thing is that I have to replace I with 1, like the values 1 to 7. So I have 7 in totals. So I can store basically this element name one by one in here. So I will start with basically writing the file, the codes here. So the person results, hot metal. So we are at 4 now. And then I can write basically the name of the element using basically the thermochemical variable here. So it's going to be $E and then underscore lowercase e and then the code number. So we start with 1 with iron, and then underscore and then uppercase N and then the $sign. So this is going to give me the name for the element number 1. Then I can do the same, so I'll just copy that for position 5 and element number 2. So you'll see quickly that doing this, especially if you have a lot of elements, so here I have 7 elements, so I would have to copy this 7 times, which is not very efficient. So again, we can take advantage of that it's basically consecutive. So I can use a loop to fill up the person results HM easier and faster. So basically I have to create a loop. I can use person 1 again, because it's my favorite variable to use for loops that are not really, that I don't need to follow up once it's done. So person 1 equal 1 to 7, because I have 7 elements and I want all their names. And then this is the command that has to be repeated. Here I see that it starts at 4, so I'm going to use a second variable, which I can use at person 2, which starts at 4, and then will be incremented every time. Okay, then so this will change to person 2. So at the first loop, it's going to be 4, and so on and so on. And this one would be person 1. So every time it's going to change over and over. So I can remove this variable because it's going to be this command because it's going to be done already. And then I close my loop. There's something I need to do in the loop here because person 1 will be incremented automatically by the loop, but person 2 is not. So I have to add one more command here. What am I doing? Person 2. To tell to the microprocessor the person 2 has to be incremented also. So I'm going to use the step command here to tell after basically filling up this, person 2 should be incremented with 1. And then when it's go back, then it's going to be 5 and 6 and 7 and so on and so on. Okay? So this is basically the name of the elements. So I have the time, the temperature, the mass of FLQ, and their composition, elemental composition. Here's going to be the names. So now I have everything ready for the hot metal. I can basically print this into the worksheet. So for that, I use the write. Again, I can take advantage of the fact that I want them to print it horizontally in the worksheet. So it means that it's going to be printed that way. So because my results HM is an array, so there's more than one entry, and it's horizontally. So I can give the entire array and then just give the first cell reference, and all the other entry arrays will be basically printed next to each other in the next cell. So now we print an LA2, so in the outputs, so LA2, and then I'm not reading, I'm writing, so write, and then I just give the reference for the first entry. So basically, I want to start in the first column, first row, because it's my headers, so the first row, so it's going to be A1. Okay? Now I need, because I created results AHM, but I don't know what is the size beforehand. But now that I've finished basically filling it up, I know that it's going to be 1, 2, 3 plus 7. The size is going to be 10. So here I need to add 10 for the microprocessor to create 10 entries in results HM. If I don't specify it, it's going to be only one entry, and it's going to basically complain when I arrive here. Okay, so we have created headers. Now I would like to know the actual equilibrium results. So I basically take the same things here, the whole block, and copy it and paste it. And then this is going to be the equilibrium results. For example, to make sure I'm not messing up with my equilibrium, I'll just kind of like indent that a little bit. It's not going to change anything for the microprocessor. It's just for myself for reading. This is the basically printing part. Okay, and now I have to adjust it. Okay, so this is our headers. Now I actually have to find the values. So the first one is a time. I'm basically at time 0 because I haven't actually started anything. So I will put 0 here. So it will just write 0 on under the time. Temperature, I will ask what is the temperature from the equilibrium file. Of course, it's going to be exactly the same as person temperature, but to make sure, I can basically find the thermochemical variable to retrieve the temperature from the equilibrium. Okay, and this is here. So this variable, $uppercase E underscore uppercase E uppercase T and $. And then I replace that string with my microprocessing variable for asking the temperature from the equilibrium. And then here I need the mass of the solution number 2, which is FELQ. So I look back at my thermochemical variable, and then I found this total grams or total mass of solution K. So basically it's the same as the name, except that the uppercase N is changed to a lowercase g. Okay, so I go back here, I change this. Of course, I don't want to have this text, I just want to have the value. And then I change the uppercase N by lowercase g. And I will get the mass of the phase of the solution number 2, which is FELQ. Now we have to define what are the element in weight percent, so their composition in weight percent. And for that, I need to find the thermochemical variable for that. Unfortunately, for elements, there is one for species. You see here, you have a species in weight percent. But for elements, you don't have that. So for the element, we need to actually make a kind of calculation, because we can see here I can have the mass of element I in a specific solution, and then I can have the mass of solution. So I can calculate myself what is the concentration in weight percent for that. Okay, so I will need to make basically a calculation. So to make a calculation, automatically I have to use the $mat function. So $mat, dollar. And then I have to retrieve the mass of element I, which is given by this macro thermochemical variable. So $uppercase E underscore, then element. I'm inside the loop, and then my element is indicated by the person1 variable, then underscore, and then it's not just the element total mass, it's the element mass inside a mixture. So then I have the lowercase m to indicate a mixture, then lowercase g to indicate a mass, and then I have to give the code number for that mixture. So this is the FELQ. So this is going to be element 1 inside FELQ, so I have to put 2 to indicate FELQ. So 2. And then close the macro thermochemical variable with $. So this is the mass of iron in the FELQ. Now I have to divide it by the total mass of liquid iron to get the fraction. So this is the total amount. So we already know the thermochemical variable for that. So it's going to be $E underscore mixture gram 2 and $. So this is a fraction. I have to multiply this by 100 to get the concentration in weight percent. Okay, and this is going to be my calculation here. So we are done. I changed the values of person result HM. Now I have to tell it where to print it in the worksheet. So of course it's going to be not in A1, because otherwise I'm going to print it on top of my headers, which is not what I want. I want to be below, so it's going to start at basically A2. Okay. So now that we have completed this, we can basically try to run it. This part of the macro, I can put, for example, an end here to make it stop, because I'm not interested in checking the rest. I know it works, but it's not printing yet, so we can just wait for the next part. Then I have to go back to my browse to get, because I'm now getcodes.mc, and then I'm checking my DeS hot metal. And you see that the equilibrium file is gone because I have a hide here, so it's not going to show up. And then here it's already finished. So it filled, you see, I can probably make it centered and also auto fit. And then I have printed the time and the temperature, so it found the values from the equilibrium, also the mass of FELQ, and the composition as well. To make sure I have I know what's the units. I could attach basically another characters here appending to the name of the elements. I could weight %. Okay, so it will basically attach weight % to each name here. Okay, but it's only a small little addition. So now we can do something similar for the Slack. So we go after the calculation of Slack init, and we start by writing the column headers. Okay, so we start with the name of the headers. So I'm going to put headers again, make sure I remember these are the headers. And then I use my results variable, which are defined here for the slag, results slag. And the first thing I want to know is the total mass of the liquid slag. So results slag, I think I wrote it that way. Is it? Where's my variable? Yeah, result. I forgot the S there. I'll just put the S to make the same structure. Okay, so now it should be the same. Results slag is the same. And then the first entry of results slag is going to be the total mass of the liquid slag. So I'm going to write again total mass of, and then I need the name of the liquid slag. So it's going to be the same again. I need to find the code numbers for the slag A. The thing is that because we have a different equilib file, the code numbers are going to be different. So we need to basically regenerate the list of codes for slag init instead of hot metal init. So I will go back to my get codes using the macro processing and then find a macro. Find the get codes.miki and then run it. And then go back to my workshop DeS. And then this time I'm selecting slag init to get the codes of that. And then open, wait a little bit, and then it will generate the codes for this one. So you can see that because I haven't put carbon in there, I have only 6 elements compared to the other ones, which was 7. And then on top of that, I have 2 solutions. It's like a number 1, it's like a number 2 because of the I option. So it means that also my solution species are going to be different because it is like A, and because of the I option, they are doubled. Okay, so there will be FES from slag A number 1 and FES from slag A number 2. And then because I selected compounds, all the compounds from the Fe oxide, then I will have also a list of species for the pure oxides. And then in total we have 48. And they start at 21. Okay, so the species here are counted right from the solution species. So here I want the name of the slag A. So this is my chemical variable for the solution name. And then the slag A number 1 is the code number 2. Okay, so I have to write $E, then mixture, and then uppercase N to get its name, and then 2 to get the slag A, and then $. Okay, so this will ask for the name of slag A, the second solution. After that, I will want the name, so I want the composition of the slag, so I want the composition in species. So basically the composition of each of these species here from 1 to 10. And actually, so I need the name of the species. So for that, I need to check what is the thermochemical variable. And then here you see that we have the species J name, and this is the corresponding thermochemical variable. So $E underscore small s uppercase N, and then the code number for the species. And the code number is already listed in the text byte here. So for compounds, the thermochemical for the species are built like 1D variable. So I can basically get the block. I can select multiple entries of the thermochemical variable at once. So here I will go to here, and then I can directly copy the species name from the thermochemical variable to the user variable in the block at once. So I will put the thermochemical variable for the species name. So species and uppercase N. And here, instead of entering the species one by one, I can specify a group of species. So I can use, for example, brackets, and then say I want species 1 to 10. So that will basically take the name of all the 10 first species at once, and then close the variable. And then here, I have to specify in which entries to put them. So because I have basically 10 entries on that side, I have to have 10 entries on the other side, except that here I'm starting at 2, because my first entry is already filled with something. So 2 to 11, to give him 10 entries to fill up. Okay. Then for the liquid slag, there is one more thing we want to have, is the elemental sulfur content of the liquid slag. Because here all the sulfur is basically kind of like distributed between different end member in the slag, and we would be more interested in knowing what is the total sulfur content rather than having the sulfur as distributed between all these compounds. So I will write first the label for that. So it's going to be person results slag 12. So this is the 12th entry. And then I'm going to write the total. So just basically a title. I'm not calculating it right now because these are just the headers. Total sulfur in weight percent. Okay, just a header. So this is all from my slag. I got the mass, I got the species composition, or here the name, and then I get the sulfur content. So now I can actually print out that variable into the worksheet. So it's going to be knowledge 2 again, and then I'm writing, and then I need to find where to write it. So this is the headers. I want it on the first row, and then I have to figure where to put it because I already have the headers for the hot metal. I want now to find it. I could, skip a column here to make it more clear where the slag is starting. So I'm going to start printing them at L. So L1 would be where I write this. And then all the 12 entries would be written next to each other. So I don't need to find out where it ends right now. The last thing I have to do is basically update the size of result slag, because now I know it's going to be 12. So I need in the declaration to specify that it has 12 entries. Okay, and then I'm going to do the same for the solids. So it's very similar. For the solids, I just want their names for the headers, because the only thing I'm interested in to print out is their mass. So here I'm just going to ask for the names of each of the species. So I'm doing the same thing as for the slag species, because the compounds, or the pure compounds as solids here, are all treated as species. Okay, so it means that I can access the values at once by just specifying the block from 21 to 68, and I will have copied the 48 species name at once into the other variable. Okay, so this one is gonna be equal to, so it's the same kind of like a name or chemical variable, except that I will have to update the block here for the code numbers for the species. So species and then names, and then now I'm going from 21 to 68. So 21 to 68. That's the block. Okay, and then I close the chemical variable with the dollar. And then here I have to basically define what is the size. I could leave it like that because actually result solid will have only these. But to be correct, you could say 1, 2, there will be 48 compounds. So the size of result solid is 48 entries. Okay, 1 to 48 should be copying and containing the names of the species 21 to 68. And then again, we know now the size of the result solid. So I can update the size of result solid in the declaration. Okay, and the last thing I have to do is basically print it into the Excel in the Excel file. So I just use the name, then only 2, and then write. And then we see that we have the result hot metal has 10 entries. Then we slag has 12 entries, so that's 22. And then we skipped one column, and then I'm going to skip one more column for this. So it means that the result solid is going to start at the 25th column inside the row, which is the letter Y. Okay, for the 25th letter of the alphabet is Y. So I'm going to write into the cell Y1. Okay. So this was for the headers. Now I need to do the same for the actual values. So this is going to be values. And then I have to find basically the corresponding entry for actually getting for each mass, for each entry of the result slag and result solid. Okay, so for the total mass of the solution number 2, then I need to get rid of text there and then find the thermochemical variable for the mass, and then for that we just need to change the uppercase N by lowercase g, and this will give you the mixture gram number 2. For the species, we want the weight percent, so we can check here the species J in weight percent. We have to use uppercase W instead of uppercase N to get their weight percent. And then the 12th entry of the results slag was the total sulfur in percent. So as we said before, we cannot get an element concentration like this. There's no thermochemical variable for that, so we need to calculate it. So we use a $mat function here because we need to basically divide the total mass of sulfur inside the slag by the total mass of slag. So we need to function here. So $mat, and then it's a weight percent, so we need to have a factor 100 to multiply the fraction it will be. And then we need the thermochemical variable for the mass of element sulfur in the slag. So for that I need my code numbers, and I need this thermochemical variable, so $E, and then this is the code number for the element and the code number for the solution where you want to have the element mass. So uppercase E underscore lowercase e for element, and then I need a sulfur. So here I find in the text file what is the code number for sulfur, which is 3. So I replace 3 here. And then I want the sulfur from the mixture in mass, so mixture gram for mass, and then I want the slag, so it's 2. Okay, and then I close the thermochemical variable with $, and then this is the total mass of sulfur in the slag. I need to divide by total mass of slag to get a fraction. And this one, we already saw it before. This is this variable to get the mass in gram of the mixture number 2. So E underscore mg to dollar. Okay, and then close the parentheses for the dollar max function. And this is giving you the weight percent of sulfur inside the slag. Then we have to update where to write it. So of course not L1 anymore, otherwise again I will write it on top of my headers. So it's going to be below, so L2. Okay. For the solids, I had the names for the headers. Now I want to have the mass. So I have to change the uppercase N by lowercase g to get their mass in gram. Okay, so that's the only thing I need to do. We are in the same equilibrium files, so all the species code numbers are identical. I just need to find the change in the thermochemical variable to get to change from name to either concentration or mass. And then again, I need to change where to write it. So I need to write it in the second row, just below the headers. Okay, then I need to remove the end, otherwise it's going to not go there. And then I will put the end there to make sure, and then run this to make sure that it's actually printing or writing the way I want it to write. So I'll go back to the equilibrium reactants and then run my macro. Again, I have to browse because it actually gets codes right now, and then DeS hot metal. And then wait for the results to be all done. Again, here it's all like weirdly put, so I will basically format to the auto-fit column, make it a bit wider. And we see here, so this was for, I added the weight percent to see the units. Then we have the total mass, and then we have the name of each species in our solution. So we have 10, which is correct. Yeah, 10. And then we have the actual concentration. In this case, we don't have any iron because we're at time 0. So it will not have any iron or sulfur at all. So total sulfur is 0, just alumina, CO2, CaO. And then we have the name of each phase and also the mass of each phase at the equilibrium at time 0. So we see here that because of the low temperature and the high calcium oxide content, we have a lot of C2S, which is formed there. Okay, so we basically finished the printing for the first time 0. So we need to do that also for the loop. So we know how these all these values changes with time as the reaction goes on. So the commands to be printed have to be done after the homogenization. So if you remember what we wanted here, we just want to know the mass and the composition after homogenization. For the metal, it's going to be R2, and then for the slag and the solids, it's going to be R3. So we go after R2. And then we need to basically keep the same structure so that they are nicely, kind of like aligned with each other. So I'm going to go there in the hot metal init and basically copy the block where I took the equilibrium results to get the same structure and then paste it after reaction 2. Okay, I can also indent it a bit more. Again, it doesn't do anything for the microprocessor. It's just for readability for yourself. And then we just update basically the corresponding the code numbers and also the values that need to be changed. So here the results run is basically the time. So this time step that is being done. So it's basically not 0 anymore. We are basically inside the loop, and the time step being done right now is basically kept by count. Okay, so count will vary between 1 and 10, and then I need to know which one it is, right? For the results, hot metal, for the temperature, it's going to be the same. And then for the mass of the FELQ, it would be wise basically to run again the get codes for reaction 2 to make sure that we have the same code numbers if they haven't shifted between the hot metal in it and the reaction 2. Okay, so we are going to run get codes, go to the workshop DeS, and then select R2 to get the codes for that reaction. Just wait a little bit, it's pretty fast. And then I can open the hot metal init, for example, the code that we got from there to compare with my R2. Okay, so this is R2 and this is the hot metal. I'll just go down, this one down. And then the hot metal and R2. So you see we have the same elements, the same solution, and the same species in the solution. So this is the advantage of including the missing elements from the initialization, because of that, like these code numbers between the initialization part and the process area will be exactly the same because I have included them. So if I didn't include it, calcium and aluminum and oxygen, all my element code numbers, so all the position in the worksheet would be different, and it would be like kind of messy to organize them inside the worksheet because they will not be. So you see the calcium has been put into an iron and sulfur. The oxygen is the aluminum and oxygen gets between silicon and carbon. So it's not like they are added below. It's like they are added based on their the molar mass of the elements. So the calcium will basically shift everything, and the aluminum oxygen as well. So that's why it's important in this case to kind of like think about which elements will come inside, so that the results can be arranged correctly from the beginning. So here we see that basically the solution, the code numbers for elements and solutions and species are exactly the same. So I don't need to worry about changing the values there. It's going to be exactly the same for the temperature, the mass of the FLQ, and even the elements number is going to be the same. The thing I have to worry now is basically where to write it. Because now I have to basically be a new row every time. So I need to use, for example, a new user variable to keep up with the row number at every iteration of the loop. So for that, I'm going to use a new variable, which is going to declare it as person row. And then I need to give him a first value, because once a variable is created, by default, it's going to have the value 0 inside. So I need to specify what's the first row where I need to print once I am inside the loop. So you can see here that my first two rows are already occupied. So I need to start with the row number 3 to be just below. Okay, so I will start at row 3. So row will start with the value 3. And then I'm going to change, instead of A2, it's going to be a person row. So person row will change every time. So this is for the hot metal values. So now I have to find the same thing for the solids. So I'm going to do the same to get the same structure. I'm going to take the block of code from the Slack initialization to get the same structure for the results. I'm going to indent it. Again, this is just for visibility, not important for the process, the microprocessor itself. And then check that basically the code numbers are the same. So for that, again, we need to run get codes for R3 this time. So get codes, go back to the workshop DeS and select R3. Wait a little minute, a few seconds to make it, and then compare it with our Slack init, which was here, to see whether we have the same phase selection, the same code numbers, whether I have to change something. And you can see that it's exactly the same. So by adding iron and sulfur, in the slag init as a reactants, I already kind of like created all the possible like species and elements that could have been created later on. So then my the results columns and the results species are going to be kept constant during the entire process. Okay, so I had 68 species being the last code numbers, so everything is fine. So I can go back to my code. So this is unchanged, the same. So the only thing I have to do basically is update where to write it. This is not going to be L2, but in L percent row. So in the first loop, percent row will be 3, so it's going to be written in L3, just below the previous one. So for the species also, we have exactly the same code numbers, 21 to 68. So I don't need to change anything into result solid. And then the only thing I need to know is to change is basically where to print it. I have to update the round number. And last but not least, before finalizing everything, I have to increment percent row by 1 using the step command. Okay, so at the end, when I finish printing everything and get ready for the next loop, I have to increment row by 1 by just using the step command, percent row step, and then you don't have to specify the value because 1 is a default value. And then this will make sure, so when we start the next loop, that row is now 4 and 5 and so on and so on. Okay, so let's now run the macro to check that everything is well and running smoothly. Go back to Equilib and File and Macro Processing, run macro, get my macro because it's not gets code anymore, and run it. And then you can see your Equilib file here, your Excel file here should be updated every time. At every calculation. So we're going to wait that it's running so we have enough data to continue. So you can see here already that the sulfur content is decreasing, and we also have a pickup aluminum, and also the silicon is decreasing. So there is some reaction happening between the hot metal and the slag. Some silicon is reducing alumina and sulfur is being picked up to the slag. It's almost done. So you can also see the advantage here of using microprocessing if you would have to do it by hand to basically create everything and open each Equilib file and calculate everything and print out everything in Excel, whereas here the microprocessor is basically doing all this manual work and annoying and time-consuming work for you. Okay, so this is finished with the 10th step. It took about 1 minute and 30 seconds to complete, which is pretty good. If you would have to do it manually, I wouldn't know exactly how long it takes, and then we check that the results are well organized. So you see it's like 100% sum, and also here to make sure we haven't forgotten anything. Quickly, 100%. So we have the total composition here, and this is the sulfur content. So it's increasing. So we have sulfur going back up. Can probably put this as general to get everything into some numbers, and then the sulfur here is decreasing. So at the end of the process here, I have about 36 ppm of sulfur left in the metal. And then we have some solids. You can see basically calcium aluminate, CaL2O4, C2S, Ca2SiO4 is created, and we don't have any other solids, 2 solids forms. And then we see also that as the process is going on, the mass of liquid slag decreases, and the mass of calcium aluminate increases gradually, as well as the one of C2S. So there is one more important thing to do here before we conclude. I will show you very briefly, so we already did this, is to check the mass balance. Because microprocessing won't check that your process flow sheet has been followed correctly and that you don't have some loss or some gain of material somewhere by forgetting to change some reactance amount in one or more reactions. So this has to be done by you, so the mass balance check. So the best is to first make an overall mass balance calculation by accounting for all the materials that is generated at the end of each time step. So here we have the mass of hot metal, the mass of liquid slag, and the mass of solid. So the sum of all the mass of these three phases should be constant and equal to the sum of initial mass of hot metal and that of slag, because we don't have any material loss or material gain in our process. It means that at each time step, I should have the same amount of total material, okay? Each phase might have difference, but if you sum all the masses, it should be constant. So let's try to do that. So I can make an additional worksheet here. You could also, make the calculation in outputs, but since the microprocessor is erasing the entire sheet every time you run the microprocessing, then I would have to enter the formulas again and again. So I will enter it in the formula in a different sheet, so it stays there. So we're going to make an header, for example, mass balance, and then write the formula. Then we go to the outputs, because that's what I want to sum up. I want to have the total mass. So I need to find the total mass of iron, which is here, okay, at time 0, because we start with time 0, plus the total mass of slag, liquid slag, time 0. We are doing it for time 0 at first. Then we need to add the mass of all the solids, okay? So for that, because I have a lot of solids and I'm not going to add one by one, I'm going to use the sum function and make a range. So from here until there. So this will basically sum all the solid mass at time 0. And then close the sum function, and we are here. So we have 105, which is what we define in the inputs, right? We have 100 metal and 5 slag, 5 tons of slag. So we should have 105, and it should stay the same during the entire process. So I will take this and copy the formula below. And this should stay at 105 all the time. I can basically also change to make it, for example, having more decimals to check that the balance is correct with more decimal. And you see that the mass balance is respected here. Okay? So there is no problem. Then we can also do the same for the mass balance calculation, but for sulfur or another element. Sulfur is easy here because the sulfur is only in the metal in the liquid slag. If I had to take aluminum, for example, I would have to calculate the aluminum in also each solids, which might be a little bit more work. So the sum of the mass of sulfur in the hot metal and the liquid slag should be constant and equal to the initial mass of sulfur in the hot metal. Because at the beginning, we didn't have any sulfur in the slag, but during the process, the sulfur is transferred from the hot metal to liquid slag. So we need to account for this too. So I will write the title here, mass balance for sulfur, and then basically put the formula for that. So we printed the weight percent of sulfur in the hot metal and the weight percent of sulfur in the liquid slag. So I need to calculate the corresponding mass of sulfur based on the weight percent and the total mass of the phase. So for the sulfur in the hot metal, I need the mass of the hot metal times the sulfur content, which is here, divided by 100, because it's in weight percent, not in fraction. And then I need to consider the sulfur from the slag. So for that, I need the mass of liquid slag times the weight percent of sulfur in the liquid slag, divided by 100, because it's a weight percent. Okay, and this should give me 0.03, which is basically the amount that I had at the beginning inside the hot metal. And then I can copy this formula for all these time steps, and it should stay the same. So which is the case here. We see that we have different values for each cell variable, and we can also basically add more decimal to make sure that we are correct. And you can see here that it's still 0.03. There is some changes here, which is basically rounding errors when we write up, because it's going up and down. It's not adding values systematically. So our mass balance for this case is correct. For example, I can now make intentionally a mistake of not updating correctly the mass of material during deposition. So let's look at our macro code. And let's say that I forgot something. I forgot to update the reaction 3. So I'm taking the slag, the whole slag, to homogenize it. So basically I will create slag all the time. And you can see the macroprocessor, of course, is not going to complain anything, because in the syntax, it's completely okay. There's no error in the syntax. There is the error in your flow sheet, but this is not integrated by the macroprocessor. So you have to check yourself if you're not making such a mistake. And the only way to do this is by systematically checking your mass balance in terms of total mass balance, making sure you don't create material. Or you can also use a couple of elements to check, to make sure that you don't have anything missing from the total mass balance. So you can see here already you have a problem. We have our mass of slag gets really, really large. And if you continue like that, it's going to be more than 5 tons, which is what was there before. Okay, and this one is going to be picked up only when you actually sum up everything and find out that, well, there is some material more, so it means I made a mistake. And then I have to check in the code one by one to see where the problem and correct that. So it's almost done. We see we already have 10 tons of liquid slag. Okay, so the macroprocessing is terminated. And then we can see here our mass balance is not working, right? So we are adding more and more material, and also the sulfur mass balance is not working. We are adding more and more sulfur in the system, which was not there from the beginning. So this is incorrect. If you have to use this to check that your flow sheet is respected inside your code. And this will not appear inside the macroprocessing window, because syntaxically this is correct. It's not checking that your flow sheet makes sense. And you have to check that something is going wrong here, and then try to change or check in the code what you forgot to update inside the reactants, for example, or what you forgot to save. It could be also that there is a typo here. It's not updating some of the streams, so you don't get an updated value when you pass it on. Okay, so that's also a possibility. So what you can do with these things later on is that you can start making graphs and graphs about the evolution of the composition of the metal, or the evolution of the mass of the phases, and so on with temperature. And you can also write, or enter different values in your inputs and calculate the simulation with different values to see what's the effect of changing the temperature or changing the reactants, so the kinetic factors, and changing the initial sulfur content or the slag composition to see what's the effect on the sulfur removal, for example. So this is about it for this application. So we'll see here, we have completed our desulfurization example. You can probably see when it's done. Make some graphs to see what's the evolution of the sulfur, for example. So it's done. Okay, so this one is our balance is correct. So we have a constant mass balance for the total mass balance of material for the hot metal and the slag and solids, and then this is the mass balance of sulfur inside the liquid metal and in the liquid slag. And then you see that it's constant, so the flow sheet works well. And then we can compare basically, or draw, for example, the sulfur. You can make charts to see how the sulfur change with the time for specific. You can also specific conditions. You can also see how the phases change with time. So if you select only the phases that are actually present, you can also make graphs, showing how they evolve with time for specific conditions. So you see here that the mass of liquid slag changes, and then the actual amount of solid calcium aluminate and solid C2S is increasing with time. And the reason for this is actually that we have a reaction. So we have sulfur removal, yeah, but we also have, so if I take this and the silicon and the aluminum inside the metal, so I can make a graph with that too. You can see that there's actually an aluminum pickup. So can I put this in the secondary axis so it's a bit more visible? So you see that basically the silicon is going down with time, and then the aluminum is going up. So you have a reaction between the silicon and the alumina from the slag. So we have silicon reducing alumina, so to produce silica and aluminum inside the metal. So basically the SiO2 content inside the slag is increasing, so it gets more acidic, and then this makes the slag composition changes. And we also have a decrease in the alumina content. So this makes changes, and then it moves the slag into a phase diagram where you get more precipitation of C2S because of the silica pickup, and also because of the change of the basicity, you get Ca2O4 precipitation as the composition changed, even though the temperature is constant. Okay, so this was the application of FactSage microprocessing to the desulfurization of the hot metal. I hope it has been useful and clear. So you see that FactSage microprocessing is definitely an important and useful tool to develop process simulation using FactSage. So now it's basically your turn to try and practice writing macrocodes. If you have any questions or comments, don't hesitate to contact me at my email address here. And thank you very much for watching.